favorite of the whole talk for a couple of reasons. So how many times have you found yourself writing ispus or something like it? Obviously, hopefully you'd use studispus. There's a few hands that have gone up here, right? And, you know, it seems straightforward. And if I would ask before I actually went into all of this, if I were asked how many compares there were going to be in the assembly instruction, I said, well, there's 4, maybe 5. I don't know. That seems to be it. You know, you have to compare against each of the characters, right? There's no getting around it. I need it, if any of those are if the character is any of those ASCII codes, then I need to return true, else it's false. Well, smart compiler engineers know better than me, which is not really hard. We have one comparison here. This is super cool, right? If I mouse over this crazy-looking constant, you can see that what it is basically all zeros with a couple of 1 bits in it. And what it's effectively done is it's built a table of Boolean values. And it said, okay, well, you know, like naively, I might write a big 256 element array of Boolean values, and then I would populate true in only the space, the \r, \n, and \t of that array. And then I'd look it up in the array, and I'd be like, hooray, branch-free programming. But the compiler is smarter, as always. The first thing it says is if it's 32, or if it's above 32, that's it comparing DIL. So the IL is the bottom byte part of the RDX register. If it's above 32, 32 is space, and all those other control codes are less than space, then it can't possibly be a space. Obviously, it doesn't know that it's a space, but it can't possibly be true. So it jumps out to the red. Otherwise, it takes that constant and it shifts it down by the actual ASCII codes that it's got. And so, and then, sorry, ands out the bottom bit. So we're basically selecting the ith bit. So it's as if it's taken my 256 byte array. It's then gone, well, there's the top 33 and above are all false, so I'll just compare that and throw it away. And then using a whole byte for each of these balls is silly. Let's bit pack it into a 33-bit value and use that. And that's what it's done. That's so cool. What's unfortunate, I will come back to this, but yeah, if that helps you visualize it a little bit more, there are just 1 bits where the character codes for things that are considered to be spaces are. We take this, we shift it down the number of times that the character is. So if it was 32 for a space, for example, we would shift it down 32 times, and that 1 bit there would end up at the bottom, and we'd be returning true. Cool. Now, the fun thing about this, I'm going to go back. Oh, whoops. If only I knew how to control slides. I think we all saw in Hannah's talk that I'm not very good at that. What if I were to switch the C, this line, and this line? This is how it used to look. Oh, that's sad. So unfortunately, we're starting to move towards the part of the talk where it's the compilers are amazing, but. And so this is one of the first sort of buts of the talk. And unfortunately, GCC, in the way it builds the parse tree, and I don't understand fully, I filed a bug and they're looking into it. It doesn't, this cool trick doesn't happen when we get the N and the R the other way around. And I don't know what triggers it, but I'm glad that I saw the good case before I saw this case. Otherwise, we would never have actually seen this example here. So it's worth checking the output of the compiler, although even though it gets it right most of the time. And for those wondering, Clang, wherever Clang is there, Clang uses the right trick, a slightly different variant of the same trick, and doesn't suffer from the reordering problem. So +1 to Clang there. Okay, where do we got down here? We saw that. All right, yeah, so as I hinted, we're now